Hey, welcome to what is going to be a new lesson. So for this one, we are getting towards the end of chapter 7. This time we're talking about growth and decay. So a few different equations we have to think about. In the past, we worked through all these different things with exponents. We talked about exponential functions and how that word is inside of this phrase here. So we looked at those graphs last time. This time we want to work on solving some problems with specifically exponential growth. There's a new equation for that. Exponential decay when we're losing value pretty quickly. So we'll see those, as well as compound interest, which is another form of exponential growth. Compound interest is interesting for a lot of reasons. There's a lot of examples with money that can get pretty intriguing when it comes to compound interest, so we will talk about that as we get to it. But first and foremost, we need to talk about the equation for exponential growth. So growth, obviously, means when things get bigger, when there's more of it over time. So here's our equation for growth. Now we see a bunch of arrows here, so let's talk about what's here. Y on the left is our final amount. A is what we start with, or our initial amount, so whatever you start with at the very beginning. We have parentheses. We have the quantity 1 plus R, and R is the rate of change. That is the rate of growth in this case. That'll always be a decimal, and R is greater than 0. So say our rate of growth was 20%. R would be 20% as a decimal, which would be 0.2. So R is always going to be that decimal. T is our time, and time is always going to be noticeable units: seconds, minutes, hours, years. So we will have time as that exponent, and that goes outside of the quantity 1 plus R. So with all of that in mind, we can look at a first example. So what we see here is a little bit of words to talk about. So don't worry about the words. We'll get to the equation in just a second. So for this context, we know in 2008, the town of Flat Creek had a population of about 280,000 and a growth rate of 0.85% per year. We're asked to write an equation to represent the population of Flat Creek since 2008. So since 2008 is important. We have our percent here. That is also important. And our initial population is also very important. So let's think about what pieces are here. We have our percent per year, and this is our growth rate. So this is going to be R in our equation. We have a population initially at 280,000. So that's going to be our initial rate, or our initial amount of people. We also know we're looking at since 2008, what is the population growth? So we know our rate, R, is that percentage. Notice 0.85% written as a decimal is 0.0085. How did we get that? Every time you go from a percent to a decimal, you have to move the decimal point over 2 units. So if you were to start here to write this percentage as a decimal, you back the decimal up once and twice, and you would get this here. So as another example, if you had 25%, that would be 0.25. You just back the decimal up twice. Okay, so with that piece aside, for this one, our decimal for our rate is 0.0085. That's going to go here in our equation. We also know our initial amount, A, is this number of people, 280,000. And the time since 2008 we have to put in as well. So there we go. With one step, just plug in what we were given. And this will represent our equation when we plug in those pieces. We can simplify it one more time just by adding 1 and our decimal. Gives us 1.0085. Everything else stays the same. So that is actually our answer. They're only asking us this time to write our equation, not to actually evaluate anything. So what is the equation? Well, if we want to know at any time how many people there are in the town, we take the initial amount, that 280,000 number, multiply it by 1.0085, and take that to the power of t, which is the number of years since 2008. So we could use this equation then to find out how many people there are at any time in the future. So our equation, and you don't need all the words, but our equation we started with was our blank one here. We plugged in our pieces here. One step to simplify. And then with a last step, our solution is y equals 280,000 times 1.0085 to the power of t. Great. So with that in mind, we could work towards applying those as we get more advanced here. Okay, so with that same type of setup, we can ask ourselves another question. What will the population be in the year 2018? That's this year. So if we were 10 years in the past trying to make a forecast for what it would be like today, we can figure that out. So in 2008, we had our initial amount. If we're now in the year 2018, how many years went by from there to 2018? Well, that would be 10 years. Simple subtraction. So 10 years went by. We also already had this equation from part A. So now where we had that t exponent, we will put in a 10. Looks like that. Now with that in mind, we could now do some calculations to actually find out that value. We're evaluating our equation now to find out the value. So what you're going to have to do is remember your order of operations. So because of PEMDAS, you would do the parentheses first. So this is already simplified. Then you move on to exponents. Our exponent is a 10. So to apply the exponent, we multiply 1.0085 to the power of 10. Exponent comes first. What you cannot do is multiply these two numbers first because you're ignoring the power, you're ignoring the exponent, and we know, based on order of operations, exponents come before multiplication and division. So we know from PEMDAS this is true. We have to work through the exponent first. So exponent before you multiply. So this to the power of 10, and then multiply by 280,000. So with that in mind, you could do the rest on a calculator, and you should arrive at this number, and you can double check that as you're working through this, either now or later as you review your notes. So 10 years later, the population of this town, Flat Creek, would be a little more than 300,000. And that is our answer. So if you use a calculator, these go pretty quick. The hard part is just plugging in the pieces, and then making sure you evaluate in the calculator the right way. So for 1B, we are done on that example. 304,731. Great. So one more type of problem that looks like that. So the idea for this one is just to write our equation. So again, don't worry about the words. We'll just talk about it real quick. So in the year 2008, Scioto School District had a student population of about 4,500, a growth rate of 0.15% per year, and now we want to write an equation to represent the population in any year since 2008. All right, so what is our equation going to be? So first, what do we know? Our blank equation is this. Y equals A times the quantity 1 plus our rate, all to the power of t. So what do we know? What of those values, those variables, those unknowns do we actually know based on what we're given? Well, 0.15% per year, that's our rate. That's our R. So we know what that is. So this we can plug in. What else do we know? Student population was initially 4,500 students. That is the amount that we started with. That is A. So we know those two things, and that is what we must plug in. So if we keep everything else the same and just plug in those two pieces, we know our amount in any year will be 4,500 times the quantity 1 plus. Now our rate is this percent, 0.15%, but we must write that as a decimal, and remember that to turn a percent into a decimal, we have to back the decimal up twice. So this will actually be 0.0015 as our rate, and to the power of t, we don't know what t is. So to finish off one more step, we can actually simplify 1 plus this decimal and just write that as 1.0015. So that being said, y equals 4,500 times 1.0015, all of that to the power of t. So if we look at our options, we see D is out. We see A, B, and C all have 4,500, but the rest of this is different. A has no T, that should disappear, so that's wrong. And if we look at B and C, what's different? Well, C has 0.0015, doesn't have the 1 like we have in our answer, so we should be looking at letter choice B, which is exactly what we found here. Plugging in those two pieces and rewriting our growth equation. And we can double check to confirm. So for 1C, your equation is y equals 4,500 times 1.0015 to the power of t. That will give us our growth to find out the population in any year. Cool. So with that aside, we can now talk about compound interest. So these equations that we're dealing with today, there's 3 of them, and they're all pretty similar. So for this one that we briefly introduced, just like the one for growth, except there's this extra n thrown in. And n for compound interest is the number of times your interest is compounded each year. You can think of it as the number of times you add on interest every year. So every time you do that, we're going to call that n. So say you compounded 4 times in a year, n would be 4. So we have r over 4 and also 4 times our power. That's the only difference. We divide by n to our r, and we take our whole thing to the power of n as well. Only difference there is those 2 things. We also changed the terminology here, but this is essentially the same thing. So we have an initial amount. We can call that P for our compound interest equation. And then the amount you end up with at the end will still be on the left side here when we multiply all these things through. So let's look at an example of compound interest. All right, so don't worry about the words. We'll talk about it once we get to the equation part. So for compound interest, this one is about college. So say Yingmei was born. Her grandparents invested $1,000 in a fixed rate savings account at a rate of 7%. So 7% is important. I'm going to put a circle around that. Also $1,000 invested. The money will go to Jingmei when she turns 18 to help her with college expenses. So, what amount of money will she receive from the investment when she turns 18? Okay. So a few things to think about. Here's our compound interest equation. So we know we're talking about compound interest. That cues you in that we need this equation. So now we have to plug in a few things here. Compound annually is also important. Okay. So what do we know based on what's in our paragraph? So the initial amount she invested was 1,000, and that is going to go right here. That is the P in our equation, the initial amount. So we know what P is. They tell us our rate is 7%, so we know what our rate is. This is R. So we know what R is. We know what P is. What else do we know? How much time goes by? Well, 18 is when she gets the money, so that would be 18 years. So we know what T is. We can plug that in. This is our T. And we also know N. So the number of times it compounds, if they say compound annually, annually means once per year. So 1 time per year, and that's going to be our N value. So we also know what N is. So everything I circled in here, we already know what it is. So we can plug in all of these things, multiply it through, follow order of operations, and get our value. So with one step of plugging all those in, it looks like this. So notice the initial amount was 1,000. Our rate was 7% or 0.07. Compounded 1 time per year, so N was 1. And then T was 18 because 18 years went by until she got the money. So we just plug everything, all the pieces in where they go. That's the hard part. From here, we have to just follow order of operations. So simplify the parentheses first. You'll get a decimal in there. And then take this, use your exponent, that's the E in PEMDAS, take it to the 18th power. And then last step, multiply through with 1,000. So once you have all those pieces, we just have to follow those steps. From here, you have to simplify as best you can, and then put it into a calculator. So one more step would look like that if you simplify. That was just adding together those 2 things in the parentheses. Then take 1.07 to the power of 18 and multiply it by 1,000. And you can confirm this in a calculator. You should get this number here. And this is dollars, since we were talking about investing money. So when she turns 18, she will receive $3,380, which is pretty cool because they only invested $1,000 to start with. So very neat. She ends up with more than triple the amount of money her parents put in by using nothing but time and allowing compound interest to work in her favor. Great. So let's look at a similar example. For this one, again, we're going to write our equation and work through it. So when Lucy was 10 years old, her father invested $2,500 in a fixed savings account. So let's label the pieces. We start with our blank equation. P times the quantity, 1 plus R over N, all of that to the power of N times T. Okay, so what do we know that's in our equation? Well, in our paragraph, we see 2,500. That's the amount then invested initially. That's our P in our equation. What else do we know? Account at a rate of 8%. So 8% is our rate. Compounded semi-annually means twice a year. So that is our N value, the number of compounds, and semi-annually means twice each year. When Lucy turns 18, the money will help her buy a car. So the money was initially invested when she was 10. So if it was invested when she was 10 and taken out when she's 18, how many years is the money compounding? Well, we just subtract. So 18, take away 10. We know the difference there is 8 years. So our time, T, we also know, and that is 8 years. So those are all our pieces. So we would plug into our equation like this. Our amount equals, and I'll change my color so we know we plugged in, equals 2,500 times the quantity, 1 plus, our rate was 8%, so I will put 0.08 as a decimal. That is 8%. 8. And then divide by N, which is 2, semi-annual. All of that taken to the power of N times T. So N is 2, T we said is 8. So we could put 2 times 8 as our power. 2 times 8. Great. So with one more step of simplifying, we know our amount equals 2,500 is what you should write, times the quantity, 1 plus 0.08 over 2, all to the power of 16. Now, from here, you need to just use a calculator, simplify the parentheses, take it to the power of 16, and then lastly, multiply by 2,500. You cannot multiply 2,500 times what's in here until you apply the power first because of PEMDAS. The exponent comes before multiplication in our PEMDAS. Please remember that. Otherwise, the value you get will be totally wrong. Okay, so start here. You have all this equation stuff down. From here, you use the calculator, plug that in, and you would find your amount to be $4,682. Now, the hard part of that is getting all the pieces in the right place. The easy part is once you have that, just plug into a calculator, get your answer. So for this one, to be $4,682. Again, it's a great way to talk about how money is being invested over time and really growing super fast. You really are getting free money by allowing it to compound over time. Great. So the third type of thing we need to talk about briefly is the exponential decay. So just like growth, things can also go away over time. So our equation for decay is the same as growth, except we have a subtraction sign between the 1 and our rate. So all that is the same, and we discussed that briefly already. Okay, so third example looks like this. Let's talk about our problem and then get our equation. So in economic recession, an organization found that its donations dropped 1.1% per year. So they're losing donations. People aren't donating as much. Before the recession, its donations were this amount. Let's write an equation to represent the charity's donations since the beginning of the recession. So in other words, we're talking about decay because we know our donations are going down every year by this percentage. So this percentage is our rate of decay. So in my paragraph, 1.1% is my rate of decay, so that's R. 390,000 is our initial amount that we had before the donations start dropping off, so that's A. And then we don't know time because we're just writing the general equation. So let's write the equation so we could then use it in the future. So we're plugging in two things, A, initial amount, R, our rate. Again, our percentage must be a decimal, so we'll work that by moving the decimal twice. Okay, so plug those two things in, looks like this. 390,000 became A, we see that here. Our rate became 0.011 because we moved the decimal back twice. Now that we have that, that is our equation. Nothing else to do. Simply plug in, write your rule. Once we get this parenthesis, that's the last thing you can simplify. So you can't subtract that through 1 minus this decimal is 0.989. And now that is the end of your equation, just written. We're basically just writing the rule so that we can apply it in the future. So that is our equation. Two things you plug in, initial amount, A, and your rate, your percent of decay for this one. That is it. Just what is our equation? Looks like this. 390,000 times 0.99 to the power of T. So with 3A done, we can look at 3B. Now we're going to apply that same equation we got. So now they tell us, estimate how many dollars we got in donations 5 years after the recession started. So take what we already had, but this time now, instead of it just being an unknown, we know what T is. T is going to be 5 years after the recession. So we have this already from our last step, part A. Now we can plug in where we had a T, we can put our 5 years because we know that is the case. So that's all that we change. Now you can use your calculator skills to get this to go where it needs to go. So take your decimal to the power of 5 first. And then once you get that, multiply by 390,000. Once more, we cannot multiply these two by each other because we have to look at the exponent first. Because E in PEMDAS comes before multiplication. So PEMDAS does not allow multiplication until you deal with the exponent. So the exponent first, always. Cannot stress that enough. Otherwise, you get a totally different answer. Okay, so with that aside, you use your calculator skills, you get this as an answer. Roughly $369,000 in donations. So notice it went down, and that makes sense because we're dealing with decay. So the hard part is plugging in. Easy part is using a calculator, get that answer. So the donations is this amount, that $369,017. So these are the type of problems you'll see today. Exponential growth, exponential decay, and compound interest. So use all the things we talked about, apply those skills, use your calculator, follow order of operations, practice these problems, and review these concepts. So good luck.